Okay, so maybe we'll go ahead and get started. Welcome everyone to the 51st ECS and Cloud Feedback Virtual Symposium, starting at noon Eastern, so about now. We're going to have, as usual, 3 AGU-style talks, about 12 to 15 minutes. We'll have time for questions after each. And then if we have time at the end, we'll have a general Q&A where anybody can ask any questions to any speakers and have some discussion. Our first speaker will be Tianle Yuan from NASA GSFC, talking about aerosol forcing from Aerosol-Cloud interactions from ship tracks to global scales. Then we'll hear from Sydney Kramer, who's at Lamont Doherty at Columbia, about low-level cloud responses to the North Atlantic warming hole. And then finally, we'll hear from Yue Dong at UCLA about the impacts of the Southern Ocean and mean state ITCZ biases. If you have any questions or comments during any of the talks, please type them into the chat at any time, or otherwise you can raise your hand and unmute after a talk has finished and it's Q&A time. And finally, this is the list of our current executive committee. Our emails are on the ECS Symposium website. So if you would like to volunteer to give a talk, if you have any questions or suggestions for how we are running things, you're welcome to contact any of us. And this is the link to the website, or if you Google ECS Symposium, it usually comes up. You can find our contacts there, videos of the past talks, the sign up for the mailing list, and more general information about the symposium. So with that, I will cede the floor to Tianle, who will tell us about Aerosol-Cloud interactions.
All right. Can you guys see the slides?
Yeah, it looks good.
Yes.
All right. So thanks for the opportunity. Today I'm going to talk about estimated forcing from Aerosol-Cloud interactions from ship tracks to global scale. Before I get into the content, I want to acknowledge the contributions from my co-authors and funding support. So as an introduction, this slide shows the kind of often seen the AI6 report in terms of forcing from different components. I'm showing the so that let me see, where do I get the pointer? The range of forcing from ACI Aerosol-Cloud interaction is 1.4 watts per meter square. It's about half of all greenhouse gases forcing so far. So that has implications for climate feedbacks and sensitivity, specifically for cloud feedbacks. If we use cloud observations of cloud radiative effects, the observed cloud radiative effects can be broken down into two major components: the true feedback turn, the W here, using PM's notation, and this is the Aerosol-Cloud interaction also contributed because they change the CRE. And when we interpret the observed records of CRE, this component should be considered. And this slide is meant to show the sources of uncertainty for cloud ERF ACI. So if we examine a cloudy scene's albedo sensitivity to cloud droplet number concentration, we arrive at three major components. These are the Toomey effect, cloud fraction adjustments to ND, and liquid path adjustment to ND. The trouble is, from many previous studies, both modeling and observations, cloud feedback and cloud liquid path adjustments to ND is nonlinear functions of background and environmental conditions. So that makes it hard to sort of constrain and pin down. One way to sort of reduce uncertainty for Aerosol-Cloud interactions forcing is to use these so-called opportunistic experiments. For review, you can see this paper, which is an excellent review. So the idea is use sort of natural experiments or opportunistic experiments to study aerosols, cloud adjustments to aerosols. And in this talk, I'm focusing on ship tracks. So ship tracks was discovered about 60 years ago from the early sort of satellite images. You see these increased cloud reflectance linear features. Later, in situ measurements sort of prove that these enhanced cloud reflectance is due to additional input of aerosols, not other factors such as water vapor or heat. So this is showing one example of measured in situ measurements of ND, liquid path, and aerosol numbers within the ship tracks and for the background cloud conditions. You can see clearly these clouds are modified by these aerosol conditions. And so we know that ship tracks are good experiments. The trouble is it's hard to find them at large scale. So what we did is we developed two methods to automatically find these ship tracks in satellite images. Like here, some examples are shown, like clear examples, but in real world, many of these ship tracks are actually hard to find. So in a paper in 2019, we developed algorithms to detect them. Then we also developed algorithms to automatically analyze them. So these three panels are showing a example of how we analyze them. So first, we start from the MODIS reflectance image. Then we detect these ship tracks from the reflectance image. And then we automatically find the control cloud pixels that's paired with these ship track pixels. Then we contrast these cloud pixels and come up with cloud adjustment functions. So examples are shown here for both liquid path on the left and cloud fraction adjustments to ND. So these functions are based on thousands, hundreds of thousands of ship tracks examples. So I won't go into the details, but if we focus on, say, one color as these cloud adjustment functions as a function of background ND, this color, you can see clearly it changes quite strongly for both liquid path and cloud fraction, especially for cloud fraction. This function almost we have a good fit for this function as exponential. So once the background clouds gets clean, the cloud fraction is really sensitive to additional input of ND. So the idea is we can use these cloud adjustment functions to kind of observationally derive how much forcing we get from ACI. So the assumption here is because these adjustment functions are derived based on ship tracks, which is about mesoscale, hundreds of kilometers long and tens of kilometers wide, then we assume that these adjustment functions apply at monthly and 1 degree by 1 degree grid scale. And so that's what we did. So we apply these adjustment functions. The ND change in this case, we are estimating the pre-industrial to present day forcing. So the ND perturbation comes from model estimates because we don't have observation ND changes from PD to PI. And we break down the forcing into these three components: TUMI, liquid path adjustment, and cloud fraction adjustments. What we see is that TUMI still dominate, but cloud fraction adjustment contribute at least about 60% of in the magnitude 60% of TUMI, while liquid path actually, in our estimate, contributes quite small. This is different from, say, modeling studies. The overall forcing estimate from our study comes to about minus 1.1 watts per meter square. It's similar to another kind of observation-based, MODIS data-based studies by Casey Wall and their co-authors. Now, because of the assumption that went into this, we have to, find ways to validate it, right? So one opportunity is in 2020, where when we kind of reduced the ship emissions over global ocean by sulfates by more than 80% in 1 year. Suddenly, in January 1st, 2020, the IMO regulation dictates that all the ships have to reduce their emissions. And so we use the same approach. What we did is use the same kind of adjustment functions, paired that with model simulated ND perturbations due to this fuel regulation. And the estimate we come up with is about 0.2 watts per meter square average odor over the global ocean. And the breakdown is between three components are shown here. Again, the TUMI dominates and cloud fraction contributes quite a significant amount. And this estimate compares quite well with independent estimate from modeling and some studies also using observations like machine learning to come up with a forcing that's also come in the same sort of ballpark. Another test is regionally. We have sort of studies by Michael Diamond and others. They look at Southeast Pacific. Because this shipping lane is kind of unique, we can observe at monthly scales and attribute changes in cloud properties to ship emissions. And for IMO 2020 for this region, Michael estimated forcing for inside this sort of core region of the shipping lane, the forcing comes about to this magnitude. And based on our estimate, our estimates is quite consistent with Michael's total estimate. So Michael's is kind of a top down because they don't consider any, why they arrived at. It's just kind of observed attributions of cloud changes or series flux changes to the ship emissions. An interesting kind of results come out of this is if we use just ship tracks alone, not considering like detected ship tracks, then the forcing coming out of the detected ship tracks is more than an order of magnitude smaller. So the implication is that the forcing from emissions are not showing up mainly through the ship tracks themselves. You have to really sort of consider the overall emissions, not just the ship tracks themselves. Ship tracks themselves are good for deriving the physics, but they are not the main contributor for the forcing themselves. Then we can find and sort of, we try to apply this to tackle why the issue of increase in energy imbalance observed by series that's also corroborated by ocean heat uptake studies showing in this figure. In recent 2 decades, the EEI has been increasing rapidly, and the main contributor to that increase is absorbed solar radiation. So in other words, the OLR actually goes in the opposite direction. And this has been a major challenge to our understanding of the kind of forcing and feedbacks, as really well summarized by this report led by Stevens et al. So they break down, sort of illustrate this EEI contributions from forcing different increase, and feedback, maybe also pattern effect. The trouble right now is our best estimates of these numbers couldn't explain this rapid rise in EEI. So there are a few ways to make these observations in concert with our understanding of forcing. Either, so for example, the pattern effect has a large contribution, or the forcing estimate is wrong. So we looked at, based on the adjustment functions and observed ND changes, as shown here. This is the climatology of ND in modus, and this is the trend. We clearly see that in recent decades, for the series period, ND has been decreasing quite strongly across many regions due to emission changes, right? Mainly from Asia, North America, and Western Europe. And this is showing the time series of global mean and different regions. The main sort of message is that ND has been decreasing, and we ask the question: given the ND trend, how much forcing do we expect from ERF-ACI? So this is kind of the summary figure. This is observed EEI change over the oceans, and we estimate that about half of that EEI change is contributed by ERF-ACI, and another half is from combination of aerosol radiation interaction and greenhouse gas forcing, and these are coming from radiated kernels derived by Ryan's Kramer and others. So during this period, we show that ERF-ACI contributes strongly to this EEI increase, and we compared our estimate to some of the other independent studies, and it appears that our study, our estimated ERF-ACI sits on the top, sort of higher end of the estimate, and we have another study that shows this with this ERF-ACI forcing estimate using this approach, we could close the gap. Like we can explain the sort of EI increase quite nicely. So now going back to the why ERF-ACI is relevant to our feedback studies, as pointed out by Priyam et al. In 2023, also in the introduction section, the observed CRE shouldn't be directly used to study cloud feedbacks, because although at grid scale, look at the color block here, ERF-ACI contribution locally is much smaller in magnitude to CRE, but average over globe, if you with the consideration of removing the ERF-ACI contribution versus the result, give you an estimated cloud feedback magnitude change by 40%. So this is a important factor when try to estimate cloud feedbacks using observations, and see more in this study. Do I still have time? I think I'll skip this slide. This is basically saying
I think if we could start wrapping up so we have time for questions, that'd be swell.
Sounds good. Yeah. So then I'll skip this slide and just go to summary here and take questions.
So does anyone have any questions? Thank you for the lovely talk. Sorry to have rushed you at the end.
No problem. Yeah.
Yes, we have a question in the chat from Rob Wood. Or not in the chat, sorry. You can unmute yourself. My bad.
Hi, Tianle. Yeah.
Hi, Rob.
My question is, did you look at all at the long wave ACI component at all? And like, how is it in any way significant compared to the shortwave?
So in this estimate, we did include the long wave, but we didn't include it as a physical component. We just roughly estimate the long wave contribution to be about 10% of the shortwave, based on Casey Wall's estimate, because their method can give you the long wave contributions, and our estimate cannot. So we just assume the 10% sort of component in the long wave.
All right. Yeah, great. Thanks.
And then we can take a quick question from Robert.
Hi, Tianle. Thanks a lot. I was curious, when you are scaling up the conditional response of like cloud fraction and liquid water path, are you using something like a radiative kernel? How are you scaling that up?
Right, that's a good question. So the details can be found here, but briefly, what we did is kind of using the adjustment functions, and we know at grid scale what sort of the counterfactual should be. So based on the delta ND anomaly, we come up with what the low cloud fraction should be if the ND anomaly is equal to 0. So that's how it's kind of like a kernel, I guess. It just depends on one thing that is these counterfactual calculations depending on the background conditions. And we consider both sort of these one-dimensional background controlling variables, but in reality, it could be also 2D, and that's where the uncertainty comes from. So depending on how we consider like these adjustment functions, depending on the 1D or 2D controlling variables, then we get different estimates.
I guess I was partly asking because I wonder if there's an inconsistency in these things, which are very sort of local in time and space, and a kernel which tends to average over all the variability. So in other words, you'd be averaging over any of the population of ND that you would have over the course of a month in that location.
Right. Yeah. So I think you're right. We have another study that sort of looking into this to check. I guess I don't know how to answer that connection to the kernel itself. I have to think about that. But so what we're doing is also trying to look at, is this assumption sort of going from local and instantaneous to 1 degree grid level monthly? Is it valid? And our results seem to show that this adjustment function at the monthly scale is quite consistent with this strip track scale. And that's coming up, so hopefully we can show that pretty soon.
Cool, that's great. Thank you. Thank you for that talk and those questions. And if anyone else has more questions, feel free to continue discussion in the chat. Otherwise, we will now hear from Sydney Kramer.
Hi, Paulina. I'm going to share my screen now. And let me know if everyone can see.
Yes, looks good to me.
Okay, awesome. So thank you for the introduction earlier, and my name is Sydney Kramer, and I'm currently a postdoc at Lamont Doherty, working on tropical cyclone risk stuff, but in the nature of the ECS Symposium and talking about clouds, I'm going to talk instead about some of the work that came out of my PhD research at the University of Colorado Boulder with Chris Karnaskis. And I'm going to be talking about a significant and robust summer low-level cloud response that we were able to find to the North Atlantic warming hole in many different AMIP experiments. So first, just to motivate our focus of study on the North Atlantic, this region is a key part of the global climate system, and it has features like the Gulf Stream and the jet stream, as well as sources of climate variability like the North Atlantic Oscillation. And these features interact strongly with sea surface temperatures in the region, which exhibit long-term trends and natural variability as well. So we're going to take a closer look at these relative sea surface temperature trends in the North Atlantic now. And this is the basin mean warming that's been removed to highlight regional structure in our sea surface temperatures in the region. On the left, you're seeing observations, and on the right is a model simulation with 2 times CO2 forcing. And both show cooling in the subpolar North Atlantic, also known as the North Atlantic warming hole, or sometimes called the cold blob. And it's a region south of Greenland where sea surface temperatures have cooled by about 0.75 degrees Celsius since 1870, despite warming oceans over the rest of most of the world. And there's a lot of debate in the literature surrounding why this phenomenon is there and how it's been so persistent. And one of the leading explanations for its presence is a slowdown of AMOC, which may reduce northward heat transport and lead to local cooling. But there's also evidence for coupled ocean atmospheric processes causing this, including air-sea interaction, subpolar gyre changes, atmospheric feedbacks like cloud effects and remote Rossby wave connections, or increased storminess in the region. And it's really important to understand this phenomenon and why it's there, because its impact beyond the North Atlantic. So in particular, it's closely tied to NAO-like variability in the region with sea level pressure anomalies. And these patterns can influence jet stream behavior and drive downstream impacts, including teleconnections to regions like Eurasia and the Indian Ocean. So my talk today is going to focus on one of the results that came out of a more recent paper that we lovingly call Cold Blob MIP. And this study is a grassroots collaborative model intercomparison effort where we brought together a number of different atmospheric models from groups across many different institutions to isolate and compare the atmospheric response to the same sea surface temperature forcing representative of the warming hole. And MIPS are really essential tools for diagnosing model behavior, identifying systemic errors, and quantifying uncertainties in the physical response of the atmosphere to different patterns of ocean forcing. And again, I'm just going to focus on one of these results, specifically the summertime low-level cloud response result that we were able to get. And if you're interested in more results from this paper that I won't have time to cover today, the full paper can be found using that QR code in the corner. So just briefly to touch on the experimental setup, we use atmospheric-only models, so AGCMs. The SSTs are prescribed, so we don't have an interactive ocean. And we use 9 different base models from multiple institutions, and we end up with 15 total different configurations to assess robustness, and I'll show that on a table on the next slide. And the key idea is that each model is forced with the same cold blob sea surface temperature anomaly forcing added to its climatology, and then we compare the atmospheric response to that forcing. All external forcings, including CO2 concentrations, are held constant at about year 2000 levels. And so this setup really allows us to isolate just the atmospheric response and directly compare the behavior across models. The experiment was conducted by each model with a control run with a climatological seasonal varying SSTs applied as boundary conditions for a large number of consecutive years without the warming hole present. And then we do a second run where we add the warming hole anomaly to it. And the anomaly that's added is time invariant. And it is, again, added to those climatological sea surface temperature fields. So this is just a table that's showing the full set of all different model configurations that we're using from the 4 different institutions. And across these, we're using different model vintages and versions. We use a range of grid types and resolutions, different vertical levels, different land and vegetation treatments, and we use different simulation lengths, anywhere from 50 to 200 years, and there is model spin up allowed in the beginning. And there's also a few different sea surface temperature climatologies that are used that reflected mostly what control runs were already available prior to running our experiments. But we have shown in the paper as well that that doesn't create any issues with our results. And one thing I want to highlight is that even when we take the exact same CESM2 configuration and we simply change the computer that it's run on, so from Cheyenne originally and then now to Derecho, the new computer, we can still get different atmospheric responses in the wintertime, which is very surprising to us and is a really fun result of this paper. But spoiler alert, even though we get a really diverse response in wintertime sea level pressure and wind responses across all the different configurations, we actually see really robust agreement across most of the summertime cloud responses that we're seeing. So To evaluate how meaningful our responses are, we take a few different complementary approaches in the paper. So first, we look statistically at whether the response stands out relative to internal variability. Then next, we look at robustness, so how consistently models agree on the sign of the response. Third, we look technically, comparing the magnitude of the response to differences in model climatologies. And then finally, physically, we assess whether any implied feedbacks are actually consistent with the underlying forcing. So to evaluate the physical significance, we ask what the atmospheric response implies for surface fluxes. So for instance, if winds change, what does that mean for latent heat flux? And if clouds change, what does that mean for shortwave radiation? And then we use a simple mixed layer heat budget to translate those flux changes into an SST tendency. And this allows us to determine whether the atmospheric response is strong enough to meaningfully impact the ocean and potentially feed back on the warming hole itself. So now I'm going to get into some results. So this slide summarizes the primary atmospheric responses to the cold blob across all of our participating models. So this is going to be the multi-model mean. The black contours you're seeing on the left show the multi-model mean response in sea level pressure. We then add colors to indicate the fraction of models with a statistically significant response. Then we add dots to indicate where the models agree on the sign of their response. And we show a white contour to mark the location of the imposed sea surface temperature anomaly. So on the left here, you're seeing a wintertime sea level pressure response, which is characterized in the multi-model mean by a weak anticyclone that sits over the North Atlantic. And accompanied by these sea level pressure changes, we're also seeing modest changes in surface wind speeds. And these circulation responses exhibit considerably more intermodal variability than I have time to discuss today. But again, if this is interesting you, please refer back to the full manuscript. But in contrast, and really the main result of the talk I'm doing today, is a summertime cloud response shown all the way on the right. And it is remarkably robust across models. So every model that was able to provide us cloud output that we had saved to look at, which is 10 out of the 15 models, so 100% means 10 out of 10 models here, shows an increase in cloud cover over the cold blob region. And the increase is modest, about 1.5%, but it corresponds to a shortwave cooling of approximately negative 3.6 watts per meter squared, or roughly a cooling tendency of about 2.8 degrees Celsius per decade when propagated through a simple mixed layer heat budget. So while the winter circulation response varies substantially across models, the summertime cloud response emerges as the most consistent atmospheric signature of the cold blob. So now I'm going to talk about how I'm getting to that low level result. So this slide is going to show the vertical structure of the cloud response with the climatological mean of JJA, or the summertime cloud cover, in the top row for the one of the control simulations from one of our models. And the response to the cold blob forcing is going to be in the row below. And the key takeaway is that the increase in cloud cover is concentrated in the lowest area of the troposphere closest to the surface, which really pops out here when we're looking at the 1000 millibar level, and we get weaker responses as we get higher up. The robust increase in summertime cloud cover is really a boundary layer cloud response, and this response is physically consistent with established boundary layer cloud dynamics, where colder SSTs, particularly in the mid-latitudes, promote the formation of low-level marine stratus and stratocumulus clouds by enhancing lower tropospheric stability and suppressing vertical mixing between the moist boundary layer and the drier free troposphere. And so on this slide, we quantify how those cloud changes translate into shortwave radiation. So on the left, we use observations to estimate the relationship between cloud cover and downward shortwave radiation. And over the cold blob region, we find a strong sensitivity of about negative 237 watts per meter squared per unit cloud cover. And on the right, you can see that that relationship is very tight with a strong linear correlation, which gives us a physically grounded way to translate the cloud increases we saw earlier into a shortwave cooling effect. So again, using those simple bulk formulations, we estimate that wintertime wind anomalies produce relatively modest latent heat flux changes of about plus or minus 1.1 watts per meter squared. But in contrast, the summertime cloud response corresponds to a much larger shortwave forcing of approximately negative 3.6 watts per meter squared. So when we propagate those through the mixed layer budgets, these fluxes imply SST tendencies of up to 0.13 degrees Celsius per decade of warming from the winds and in the wintertime, and roughly 2.8 degrees Celsius per decade from clouds of cooling in the summer. So notably, these values are on the same order as or even larger than the historical warming hole trend itself. And this suggests that atmospheric feedbacks, particularly those associated with summertime cloud cover, may play an important role in the persistence of the North Atlantic warming hole. So I'm just going to leave these summary and conclusions up. But basically, the point of this paper is just to show that the warming hole drives small but robust atmospheric changes. And the wintertime circulation responses vary greatly across models. But every model that we have cloud output for exhibits this increased summertime low-level cloud cover. And this response corresponds to a cooling, and that dominates the wintertime warming response. So this suggests that atmospheric feedbacks may help sustain the warming hole. So with that, I'll take any questions.
Great, thank you for that excellent talk. If anyone has a question, feel free to raise your hand or put it in the chat. Andrew has a question. Go ahead.
Sorry, one sec. I can't.
Oh, sorry, it's not in the chat. You can.
Okay.
Andrew, you can unmute yourself.
Can you hear me?
Yes, I can hear you.
Yeah. Hey, Sydney, great talk. Thank you for that. So the SST anomaly that you put in, that's like the same in every month?
Yes, so it is time invariant, but the climatological SSTs are still able to vary. But the actual SST anomaly that's added stays exactly the same year round.
Is that like, so I don't know what the blob looks like seasonally. Is the blob kind of like a seasonally invariant, like negative SST anomaly, or is that like does that represent the observations? Well, I don't know.
Yeah, there is a little bit of variation between winter and summer. It tends to get a little bit cooler in the wintertime, just also when the jet stream is stronger, and the winds are faster there on the surface. But for the most part, yes, it is always a negative SST blob, cold blob of water. So for the intents and purposes of this study, we leave it exactly as is for every season. And of course, it's not able to respond to the atmospheric changes because it's an AMIP model. So hopefully that answers your question.
Yeah, great. Thank you.
Yeah, of course.
And then Lily Han was next.
Hi. Yeah, thanks for a great talk. You mentioned that the cloud changes were a result of changes in stability. And I'm wondering if you also looked at the role of any changes in the jet for these cloud changes. Yeah.
So we actually noticed in our winter time response that the jet is playing way more of a role because it's stronger in the wintertime. We didn't notice as much of a sensitivity to the jet stream in the summertime response. We actually get a really weak sea level pressure and wind response in the summertime. So that's not our explanation for the cloud response that's happening in the summer, but we do look at the jet stream a lot in the wintertime response. So I welcome you to check the manuscript to look at that.
Okay, great. Thanks.
Of course.
And we can finish with a question from Chris Brotherton.
Hi, Sydney. Great talk. I was wondering, since this seems to be a very robust model prediction, have you looked for it in observations too?
Yes,
The increase in cloud?
we have. I believe so. Funny enough, we were really motivated in this project to look at the wintertime response. So the summertime cloud response was kind of like an extra cherry on top that we weren't expecting. And so we actually look a lot in observations for the wintertime response and sea level pressure and wind changes, but we have not looked at the summertime cloud response and observations. So that would be a really fun thing to do next. Great suggestion.
Thanks.
Great. For the sake of time, we will move on to our next speaker. But as always, feel free to continue discussions in the chat. And again, thanks for your great talk.
Great, thanks.
And up next, we have Yue Dong. So take it away.
Yeah, thanks, Paulina. Yeah, you can see the screen, right?
Yeah.
The full screen?
Yeah.
Cool. Yeah, thanks so much for having me. This is to change the research topic from the North Atlantic in the previous lovely talk, to the broader large-scale SST pattern. This work focused on the remote tropical impact of the Southern Ocean, and we find the strength of the Southern Ocean teleconnection is largely modulated by the mean state ITCZ structure. Therefore, it could be largely underestimated in current models due to this mean state so-called double ITCZ bias. This work was motivated to understand this observed tropical SST trend patterns, this La Nina-like SST trend pattern, and well-discussed model biases. Nicely summarized in Wills et al. Paper. But I would like to draw your attention also to the Southern Ocean, this part where observations also show pronounced cooling while models show systematic biases. So this prompts to this idea or hypothesis that the observed tropical cooling might have been in part driven by the observed Southern Ocean cooling. And this has been tested in a series of modeling studies where you impose or perturb the Southern Ocean in a GCM, and you often see tropical SST circulation, precipitation responses. And the associated mechanisms have been nicely summarized in this Kim et al. 2022 paper, involving a series of atmosphere ocean coupled process, such as mean state winds in the Southeast Pacific, triggering the initial advection, SST advection from the Southern Ocean to the tropics. Now, once you have established initial SST perturbation in the tropics, it could be further amplified by a lot of positive feedback, including wind evaporation SST coupling, the west feedback, the radiated effect from low clouds in the Southeast Pacific, and also coastal upwelling. Especially the role of cloud feedback, the radiated effect, has been emphasized in a lot of recent studies, especially in those models with significant cloud feedback improvement. But I can see the winds are also playing a big role here, both the mean state wind in this region and also anomalous wind or wind response to SSTs. And we know in this region, the subtropic, the tropics, winds are tied to tropical convection, precipitation, and the circulation. So in this talk, we ask, what about the role of the tropical mean state, especially ITCZ structure, in setting the strength of the Southern Ocean to tropical Pacific teleconnections? Specifically, in a single model, if we correct the mean state ITCZ bias, then does it change this model simulated tropical response to the Southern Ocean forcing? And if so, does it also exist in other models? And essentially, this ITCZ modulation, does it contribute to the intermodal spread in the model simulated Southern Ocean teleconnections? And finally, if yes and a yes, single model, multiple models, then what are the implications for the observed tropical SST trend and model biases? So we start with a single model, our slab ocean version of CES-1. This is a mean state of this model. We use radiated forcing fixed at present day climatological levels. Now we also take Q-flux climatology from the apparent fully coupled CES-1 PI control simulation. So it contains all kinds of pretty typical model mean state biases. And then we impose this regional Q-flux surface forcing in the part of the Southern Ocean to thermally force the Southern Ocean to cool. And this model simulates this tropical La Nina-like SST response to this Southern Ocean forcing. So this typical Southern teleconnection, first reported in my previous paper, but also consistent with other studies in other models. But as I mentioned, this model, this mean state has, because it's taken from the fully coupled PI control simulation, and contains especially the double ITCZ bias. So here I'm plotting the zonal mean, annual mean precipitation mean state in observations in red, and in this model, the black line. So you can see observations show more intense precipitation in the northern hemisphere and the less in the southern hemisphere, while this model just shows two symmetric zonal mean precipitation compared to observation. And this is not unique to CES-1. If you look at SIMI-5, SIMI-6, across models in general, they just show too much precipitation in the Southeast Pacific sector and too less in the southern hemisphere. So again, in general, too symmetric precipitation. So in this slab ocean model, we can fix that by modifying the Q-flux climatology, so sort of nudging the surface flux to force the SST mean state towards observations. And by doing so, now our mean state, zonal mean precipitation, this blue line, is in better agreement with observations, more asymmetric. And spatial pattern shows much more reduced precipitation bias in the southern hemisphere and increased precipitation in the northern hemisphere. So now in this model, we have two mean states. One is just a default fully coupled model with double ITCZ bias and associated SST winds biases. The other is by modifying the Q flux in this model is closer to observations. So in this model, we can use two very different mean states, but adding same amount of the Southern Ocean forcing over the same block in the Southern Ocean. And we can evaluate the resulting tropical SST response. And we find this La Nina-like response is much stronger in this correct or ITCZ corrected simulation. So what drives this additional cooling in this region? So take the difference between these two experiments in the response, highlighted here, and then we apply this mixed layer heat budget analysis, looking at different individual components, especially the latent heat for the decomposed to individual contribution. And we find overall the shortwave effect associated with low clouds and the latent heat effect associated with wind anomalies, which indicates the west feedback are the two most leading contributors to this additional cooling associated with correct ITCZ. But if the spatial patterns further highlights that the cloud-rated effect is pretty much limited, mostly confined of the coast, while the contribution from the enhanced west feedback is more pronounced and broader and stronger to the in the broad trade wind regions. And this is because when we correct the mean states precipitation, now you have a more enhanced convection in the northern hemisphere, reduced precipitation bias in the southern hemisphere, allowing stronger southeasterly mean state winds and cross-equatorial southerlies in the mean states. And this strengthened mean state winds now can generate stronger mean state advection and stronger west feedback, therefore driving additional cooling response. So in this model, basically we find if we correct the mean state ITCZ, indeed we find stronger tropical ST response for the same amount of Southern Ocean cooling. And then the next question is, does this hold in other models? Does it help understand the intermodal spread in model simulated tropical response to various Southern Ocean forcing? So we turn to this very interesting two multi-model compared to MIPS. One is called 18 MIPS, where models are forced by radiative forcing over the Southern Ocean. So they impose the solar flux anomalies in the Southern Ocean. So radiatively cool the Southern Ocean SSTs. And the other is called SOFIA, the freshwater forcing, where models are forced by additional freshwater input from or in the ocean model to mimic or study the Southern Ocean response to Antarctica ice sheet melting. So very interestingly, these two MIPS focus on totally different process. One is thermal forcing, as I highlighted here. One is freshwater forcing, but they both focus on the Southern Ocean and use different forcing drive the Southern Ocean cooling. So I look at these different MIPS and focus on the remote tropical SCT response. And to ask these models, in general, these are two multi-model mean show some tropical response. But if you look at individual models, they show varied degrees of tropical response. So the next question is, do models simulate different degrees of tropical response due to their different mean state ITCZ structures? So to quantify that, we'll look at their mean state precipitation. And we define this precipitation, let's say asymmetric metric. Compared with observations, this is just a difference between zonal mean, between the northern hemisphere, southern hemisphere in the zonal mean precipitation. So more asymmetric precipitation or larger index meaning is closer to observation, while smaller index means too symmetric, then too double ITCZ, too much bias. And then we plot each model's mean state precipitation index versus their simulated tropical SST response averaged over this white box across two MIPS. So here, two MIPS to plot. Horizontal is their precipitation asymmetric index, and vertical is their simulated tropical ST response. So you can see, even though they apply totally different Southern Ocean forcing, but they both show very strong correlation, showing you, in general, more asymmetric precipitation or larger the index is, or more realistic ITCZ mean state on the horizontal, usually correspond to stronger tropical response, tropical ST response, tropical cooling response, or tropical ST response per degree of the Southern Ocean cooling. And the mechanism seems pretty consistent with our CES-1 slab ocean simulations. Take an example as SOFIA models. If I do intermodal regressions onto this precipitation index, we find Again, more asymmetric, meaning that their precipitation patterns are in better agreement with observations, more intense precipitation in the northern branch, reduced biases in the southern hemisphere. Therefore, in the mean states, there are stronger winds, southeasterlies and cross-equatorial southerlies. And this mean states drive stronger trade west feedback in the broad trade wind regions, therefore allowing stronger tropical SCT response to the same amount of Southern Ocean cooling. So now we can see in single model, if we actually correct the models or looking at the intermodal spread, there seems a robust modulation of this tropical response to Southern Ocean by the mean state ITCZ structures. So the next question is, what are the implications for the transient observed SCTs? Because we know all models share this double ITCZ biases. So lastly, we turn to these transient simulations, historical simulations by the GISS model. Again, this is the observed SCT trend over recent decades. Broad Southern Ocean cooling, tropical cooling, and this default GISS model historical ensemble mean with significant bias in the Southern Ocean and tropical Pacific. And we turn to this unique, their new ensemble involving this observationally conserved meltwater input from the Antarctica ice sheet melting. So by adding the meltwater inputs, they find the Southern Ocean SCT trends got much improved. But if you take the difference between these two, which highlights the meltwater impact, you can see, well, this figure probably shows you the meltwater effect is largely confined over the Southern Ocean, because you don't see much tropical response. So you may infer, well, the meltwater effect is really limited to explain the observed tropical SCT trends. But we find this model happens to have very large double ITCZ bias. You can see it's very typical double ITCZ. Also in the Sophia ensemble, this is where the GISS model is. You can see a very biased precipitation mean state. And we know observations are here, very asymmetric. So it can almost be like emerging constraints or observational constraint to say, if the model had reproduced this observational precipitation mean states, then based on the regressions, then this would have been the level of tropical response to the Southern Ocean cooling that the observation suggests. So we incorporate this adjustment to this model using their precipitation and their regressions we got from Sophia model. We can see even with the same amount of a Southern Ocean cooling response to meltwater, now with the corrected ITCZ mean state biases, now the model can simulate much stronger tropical SCT response. So suggesting that correcting mean state ITCZ definitely have large implications for understanding the observed tropical SCT trends and model biases. Yeah, so this brings to my conclusions. We use a series of modeling evidence, including single models or multi-model comparisons. We find there's a robust modulation of the Southern Ocean teleconnections by the mean state ITCZ. So the models with more realistic ITCZ tend to simulate stronger and better patterns of surface winds, especially the southeasterly winds. And these winds are key to driving the tropical response through the west feedback. And since all the models share this persistent and systematic double ITCZ bias, then this implies that the current simulated tropical response to Southern Ocean forcing, various forcing, freshwater forcing, thermal forcing, or ocean circulation could have been largely underestimated. So it's still important to understand how mean states modulate the climate change signals. Yeah, our paper recently got published. I'm happy to take questions. Thanks.
Great, thanks for the wonderful talk. Yeah, as usual, people are free to raise their hands or put questions in the chat. I see a question from Matt.
Hi, Yue. Nice talk.
Hi, Matt.
Kind of a two-part question. First, when you were doing the flux correction, were you correcting it kind of zonally, or was it kind of a zonal mean correction to try to shift the ITCZ latitudinally? And then with that in mind, when you were around slide 13, 14, you said you were talking about WES and shortwave in that triangle, but it seemed like the biggest impacts were in the Western Pacific and the convective region. So I was just wondering if you could talk a little bit more about kind of zonal asymmetries here.
Yeah, the first question is in the flux correction, not just by imposing the zonal mean heat flux, we're actually doing more specific local point flux correction by nudging the Q flux towards a new mean state got from another fully coupled flux corrected simulation. So essentially, we're nudging to observations. So not just a zonal mean, actually, a gray box over the open ocean.
Great.
And then great catch on the West Pacific. Indeed, I didn't spend much time talking about this. I think it's also associated with the precipitation pattern in this flux corrected simulations. You see here. Yeah, so there are definitely also some resulting precipitation changes in the West Pacific, which might lead to this additional anomalous SST and living heat effect in the West Pacific, which, yeah, I would probably need to dig it more into. Great question. Thanks.
Thank you.
Any other questions? If anyone has any questions for any of the speakers, now's also your chance. Yes, Andrew.
Anyway, that was a fantastic talk. Thank you.
Hey, Andrew.
I really like the bit at the end where you like correct for, you know, accounting for the regression as well. This is like a bit of a weird question, but have you seen, basically, I saw this paper recently by Sarah Kang and some of the people at MPI where they had like the high resolution model and like, you know, they have this one ensemble member and it looks really, really good. But then that model has like an incredible double ITCZ like bias, like as bad that or worse than a Siemens model. So I don't know it's not really a fair question because you're not on that paper, but I don't know if you have any thoughts about like the relative role of maybe like the double ITCZ bias versus like maybe other biases that the models might have.
Yeah, that's an
open-ended question. Sorry.
Yeah, that's a great question. Actually, I've also thought about this. So in our well, I think the literature suggests the cloud feedback is definitely key. I think also the MPI model, I think they find a much improved cloud feedback, therefore stronger tropical response to the Southern Ocean. Also in CS1, CS2. And here we find the double ITCZ, the West feedback, so play a role. Actually, I've wondered that myself, and in the paper, we actually provide two experiments. One is to explicitly correct the ITCZ, like the experiment I showed here. Now, one is we dig into radiation code and the change or improve the cloud SST sensitivity based on satellite observations, a code developed, I don't know if Philip is still here, I think he's online here, by Paulo Chepi and Philip Buren in the UK. So in the radiation code. So we actually provided two experiments because I wondered if changing ITC mean state could lead to changes in the cloud feedback, or changing the cloud feedback could lead to mean state improvements, and what are their relative roles. In our experiment, we find they act more independently. Correct ITCZ doesn't really, well, in this model, doesn't change the cloud feedback. Or when you change in the radiation code, change the cloud SST sensitivity, doesn't lead to significant improvement in the SST mean state and precipitation mean state. Although I think if you look at CMIP intermodal correlation, there's some weak correlation, but I think a model physics space, they're probably governed by two separate or some separate process. So I think this might also implement the MPI model. You have the improvement in cloud feedback, but doesn't necessarily guarantee the improvement in ITCZ. And may need effort to improve both.
And in your CSM1 runs, if you improve the SST cloud sensitivity, do you also get a stronger response to Southern Ocean forcing as well?
Yes, driven by a cloud-related effect.
Cool, thank you.
Yeah, great questions.
Yeah, thank you everyone for your questions. Thank you to our speakers once again, all three of you, for your great talks. With that, we are right on time. So obviously, if people have more questions, you're free to continue to discuss. But otherwise, thank you so much for coming to our 51st ECS Symposium, and see you next time.